Hey friends, there are many things that Jesus is and many things that he is not. One of the things that Jesus is not is a quitter. It's not in his vocabulary at all. And so Paul was able to write to the Philippians that he was confident that he who began a good work in you will carry it on to completion until the day of Christ Jesus. I'm a work in progress. God isn't finished with me yet. I hope you're a work in progress as well, but one thing we can be sure of is that Jesus won't stop until we're the people that he's designed us to be. This lesson is on section 11.1, the first part. On Brightspace, there is posted a note packet and a spreadsheet. The note packet looks like this, and the topic is indeed Monte Carlo simulation, which is a way of using random number generation to estimate probabilities and things related to probabilities that we want to know something about. It takes examples to understand that. So what I want to do is, first of all, give some examples of how to generate certain kinds of random numbers, then an example explaining kind of what Monte Carlo simulation is and why it works, and then a couple of examples similar to homework questions that illustrate the kinds of things that you should be able to do. First of all, random number generation. So I think just a little bit we've used the RND function in Excel. What that does is generates a random number with a uniform distribution on the interval 0 to 1. When I use rand, I always have to put empty parentheses after the command so that Excel knows that it's a function name. Now, the first problem, problem 1, asks about random variable w, which has a uniform distribution, but not on 0 to 1, but on 1 to 5. So here's how I can use the output of rand to tweak it a little bit. First of all, notice that the length of this interval is 5 minus 1 is 4. And so the next thing that I'm going to do is multiply the rand command by 4. And what that does is generates a random variable now not on 0, 1, but on 0, 4. But I didn't want 0, 4, I wanted 1, 5. And so if I take this interval and scoot it over by 1, then I will get the random variable w that I was talking about that is uniform on 1 to 5. So what I really want to do is 4 times rand to get the right length first, and then add 1. And now that will produce random numbers according to the formula that I want. Let me go into the worksheet now. Section 11.1, simulation. There are 4 tabs that are already built, and so for most of these examples, I'm going to try and do them here, recreate them for teaching purposes. But if I get stuck or bogged down, I can go to these tabs, and you obviously can look at them too. So I'm going to save a few blank columns here that we'll come back to in a moment. And then let's put random variable w. And we said that we would like to implement this as 4 times a rand command and then plus 1. So if I drag this down a ways, 20 rows or so, here are 20 random variables. You notice that they're all between 1 and 5. And if I were to make a histogram of these numbers, I would expect to see a roughly flat distribution like we ask for. Number 2 says, I want a random variable y that has a normal distribution. So we'll start with rand again, having this flat distribution. And this time I want to take it to a random variable that has a bell curve with peak at 30 and standard deviation 5. We've used the normal inverse command before. This time we're going to put a random number into it. So rand generates a uniform random variable in 0, 1, and the normal inverse command turns it into a normal random variable with the right mean and standard deviation. Let's implement variable y with a norm dot inverse command. And the first thing I give it is a random variable. The second thing, mean 30. Third thing, standard deviation 5. And drag that down a ways. Here are random variables that are somewhat close to the number 30, and if I generated a histogram of these, I should expect to see roughly a bell curve. Finally, we want the random variable x. Now, x is different. It is a discrete random variable with specific probabilities. So x can only take on the values 2, 4, or 5, and it should do so with these probabilities. So now I'm going to come back and use my first columns here. I'm going to divide the interval 0 to 1. In fact, I'll illustrate that on the worksheet here. We're going to take the interval 0 to 1. I'm going to draw it way stretched out here. And what I would like is to cut it into several pieces like this, so that this has area 0.3, this has area 0.1, and this has area 0.6. Now, to make these numbers work out, remember this height is 1, so to make these numbers work out, this boundary has to be the number 0.3, and then to get another 0.1 area, I'd have to go up to 0.4, and then to get another 0.6 area, I have to go up to 1. So 0, 0.3, 0.4, and 1 are the boundaries of intervals into which I'm slicing the main interval 0 to 1. So there's going to be an upper and a lower boundary for each of these subintervals, then a column for the actual number and a column for the probability of that number happening. Let's fill in the numbers first. The only possible values are 2, 4, and 5, and they should happen with probabilities 0.3 and 0.1 and 0.6. Now we're ready to construct the boundaries. We start at 0, and then the upper boundary of a given class is the lower boundary where I already was on the interval, and then add the probability. Then on the next class, the lower boundary of the next class is going to be the upper boundary of the previous class. And the upper boundary of the next class is its lower boundary plus the extra probability that I'm trying to get. And then by now the pattern is set, and I can just drag these formulas down. I should double check that my last upper boundary is 1, and then so the process has worked. I've successfully cut up the number, the interval 0 to 1. Okay, now let's come over and generate random variable x. What we're going to do is use a VLOOKUP command. We did this near the beginning of the semester. The value that Excel is supposed to look up will be a random number. Then I need to give the table where these values are stored. So it's those cells, and I'm going to be copying this. So let's make these absolute addresses. So generate a random number, then look it up in this table. The next thing Excel wants is which numbered column should I return? So in this table, the first, second, third column has the actual value that Excel is supposed to get. And the fourth should be true. What we're saying here is telling Excel, well, if you have a random number like 0.2, it's not in the table. What you're really supposed to do is round down. That's what the true means. And call that a 0 so that I return the correct number. So generate that and drag it down. And this looks good. Here we have a column of 2s and 5s and 4s. And what you should see are more 5s than anything else because that had the largest probability. Not many 4s because that had the smallest probability, and so on. So it looks like that command is working. Let's do an example now that illustrates what Monte Carlo simulation is and why it works. So here's kind of a definition. We'll call something Monte Carlo if it consists of repeating a trial many times with random numbers and then count the number of successes that we obtain and use some sort of proportionality. Let's look at an example. Suppose I have the curve y equals 4 minus x squared. It's a parabola. I'm just interested on the interval 0 to 2. And so here's the little chunk of the parabola that's for x between 0 and 2. And now, for whatever reason, I want to know the area in the first quadrant. So coordinate axis here, origin here. I want to know the area in the first quadrant that's under this curve. That's actually a problem that's best solved by calculus, but let's use Monte Carlo simulation to illustrate the method. So what you need to do is find a person who is really, really bad at darts, and then also print this out large and put it on the wall. And then you have the person throw darts at this a figure. The blue dots here are the result when I did that. And the reason that the person has to be really bad at darts is that they shouldn't be trying or able to aim at a bullseye. They should be randomly throwing darts at any area of the any region of this rectangle. So it's just as likely that a dart would land here, as here, and so on. In other words, the location of the dots is uniformly distributed. So let's show how that could work. This is the only spreadsheet that I'm not actually going to build because we won't have to do things like this, but I just want to show how it works. So on the right, I've just generated some numbers that let me graph the parabola. All this stuff over here is doing is graphing the orange parabola. Then I threw darts by generating random numbers. So in the column for variable x, x should be a number between 0 and 2, the x coordinate of one of these data points. And so I took my rand command and multiplied it by 2. And y should be a number between 0 and 4, so I took my rand command and multiplied it by 4. Then when I take these x and y coordinates together, they generate a point, and so I graphed all of the 20 points that I generated, and here they are. Again, some of them fell above the curve, some of them fell below the curve. Then in this column, I built an if command. So what this is checking is if the quantity for y, if the y coordinate is less than 4 minus the square of the x coordinate. So Excel is just checking if y is less than 4 minus x squared, which is exactly what I want to do to check if a point is under the curve. If so, return a 1. That dart was a success. It landed under the curve. If not, then return a 0. That dart failed. It did not fall under the curve. Now, what am I going to do with these numbers when I get them? Well, I'm going to set up a proportionality relationship. So I'm going to count the number of points or darts below the curve, below the parabola, and divide by the number of points total. And if these darts are landing randomly, the fraction of the darts that land below the curve should be the same as the fraction of the total area that's below the curve. So area below the curve divided by area total. Well, area total of what? That means the area of this whole box that I was throwing darts at. And it's a rectangle, so its area is 2 units wide times 4 units tall. It's 8. So I can easily get this total area number, and by counting, I can get the number of points below and the number of points total. Then I know 3 things out of the proportion, and I can solve for the 4th thing, which is what I'm trying to find, the area below. So let's have Excel do the counting as well. Now that I've generated 20 trials like this, I come down here and I'll use a COUNTIF command. So COUNTIF takes 2 things. I have to tell it where the data range is, C2 to C21 for me. And then what am I supposed to be looking for to count? So in quotes, equal 1. Count the number of values in this range that are equal to 1. Excel did it. It got 11 in my implementation. If you're building this yourself, you probably got a different number because the numbers are randomly generated. Then the probability is the count that were equal to 1 divided by 20, which is the total number of darts that I threw. Okay, so that's implementing this. And finally, if I took this equation and solved it for area below, it would be to multiply both sides of this equation by total area, or 8. And so in the spreadsheet, I have taken the probability in the cell right above and multiplied it by 8 to get an estimate of the probability. Okay, let me show you something else. This is the number, these are the numbers that I got this time. If I have Excel do a recalculation, lots of things happen. So notice when I do this, I'm just typing a number to force a recalculation. Notice that the points are again randomly generated, so they move all over the place. And different numbers of points can be above and below. And then as I'm doing this, these numbers here are changing as well. The count of the numbers below and the corresponding calculated probability and area are changing. So what I want to do here is just generate a few of these and look at what's happening to the area. So now I note that I got a 5.6, I got a 4.4, I got a 6, I got a 5.2, I got a 5.6, and so on. These numbers are jumping around a bit, not terribly much, but some. So come back here and I'll say that the area is approximately equal to, well, let me give a range actually, since they are jumping around. Area is between, and I was getting numbers somewhere between 4 and maybe 6.5 or so. I think the true area is somewhere between there. Now, this is not a very accurate range. If I want a more precise estimate, the thing to do is throw more darts or generate more points. Here, I only generated 20 points, and so I'm getting some bouncing around in my estimate when I regenerate. If you want good estimates, then don't generate 20 points, generate 1,000 points or something like that, and then these numbers will not change as much and you'll get a more precise estimate. So that's what Monte Carlo simulation is. To summarize, I randomly generate some values. that's in this problem corresponds to throwing darts or putting points on this region. And then I calculate the number of successes that I got, and then use a proportionality to calculate some quantity that I'm trying to find. Now let's do two more examples. Both of them are very similar to homework questions, actually. So here, I'm going to throw 3 regular 6-sided dice. And I want to estimate the probability that the sum of the numbers is more than 12. Okay, so pretty simple question that I want to do. Let's start a new spreadsheet. And what I want to do here is, well, first of all, notice that a dice has values 1 through 6. So to simulate it, I'm going to generate a random number that takes on the value 1, 2, 3, 4, 5, or 6. It's a discrete random variable, in other words. So I need my setup for a lower bound and upper bound, the number, and the probability. And this time the numbers can be 1 through 6, and the probabilities are actually all equal because this is a fair die. They're all equal to 1/6. So I will take that and drag down. Now let's build our boundaries. We always start at 0 for the lower boundary of the first class, and then the upper boundary of a class is the lower boundary plus the additional probability. The lower boundary of the next class is the upper boundary of the previous one. The upper boundary of the next class is the lower boundary plus the probability. And now the pattern is established, so I can drag these down, and I finish at 1. So here are my cutoffs, the regions when I should tell Excel to call it a number 1 through 6. Now let's generate some dice. So there are going to be 3 of them. I'll call them die 1, 2, and 3. And here is how I want to build it with another VLOOKUP command. Look up a random number in let's see, on Excel. In this table with absolute addresses, go into column 1, 2, 3 to pick off the actual number and make it be true that you round down or use approximate values. So there is the outcome of 1 die, and then if I drag this down, should be okay since I used absolute addressing. So here it's showing that, okay, you generated a die roll that was a 6, a 1, and a 6. And if I regenerate, there's a 6, a 2, and a 5, and a 5, 5, and a 4, and so on. What I'm really interested in is whether the sum is greater than 12 or not. And so let's add these together. And here is a sum that's actually exactly equal to 12. Now, I'd like to do this 1,000 times to get a good estimate. So let's come here and start a data table. Here's a trial, and here's the sum on that particular trial. I want 1,000 trials. So this is a little bit clunky, but if I start 1 and 2 and then highlight those and now drag down, doesn't matter exactly how many you use, but I want close to 1,000, and you have to know exactly how many you used, whatever it is. So I'm going to actually make it be exactly 1,000. So we're getting close here. And I think about right in here. And I got a couple extra, which I will clear. So now I have exactly 1,000 numbers there. What do I want Excel to do? To calculate a sum of a die roll. And now let's have Excel fill out the rest of the table. If I highlight the first two, the two columns in the first row and do a Control-Shift down, it will highlight the rest of the table that I'm trying to fill in. And now let's make a data table. I don't think we've done this since early in the course, but if I go to Data and What If Analysis Data Table, I get this dialog box. Okay, this table only has one column, the actual values that it's filling in. So there is no row input cell. I should leave that blank. And for a column input cell, that's actually being controlled by the rand command. So literally what I have to do here is give it something, but it doesn't matter what I tell it. I don't want to give it, I don't need to give it any information. The best thing to do is literally to just click some blank cell so you're sure not to mess anything up. Again, I have to give a cell reference here in the column input cell, but it's not needed any particular value. So click on some blank spot and then click OK. And here Excel has filled out the table. So on the first trial, I got a sum of 7. Second trial, got a sum of 10. Third trial, sum of 11, and so on. Now, what am I supposed to do? Estimate the probability that the sum of the numbers is more than 12. Okay, so let's do that by, first of all, count if greater than 12, and then an estimate of the probability. For the count, I'll use a count if command again. I will give it this range of 1,000 numbers, B11 through B1010. And what is it supposed to be checking for if the number is greater than 12? Put that in quotes. Press enter. And finally, for a probability, it's the number of successes, the number of counts greater than 12, divided by the total number of counts, total number of trials, which for me is 1,000. So now I'm getting numbers like 0.279, and if I have Excel do some repeats here, 0.261, 0.261 again, 0.276, 0.288, 0.260, and so on. Okay, those numbers are jumping around a little bit, but not very much actually, because I have a large number of trials. So I think I'm pretty comfortable coming back here and saying that the probability that the sum is greater than 12 is approximately equal to, and I think 0.26-ish was the number that I was getting most often, or the numbers were closest to something like this. If I wanted more an accurate number, then instead of using 1,000 trials, I could use 10,000 trials or 50,000 trials. If you do, actually, you notice that Excel starts to slow down, though, because the number of calculations that it needs to do are so large. Okay, third question, very much related to one of your homework problems. A company produces car batteries, and what it knows is that the average lifetime of the batteries is 48 months. The standard deviation of lifetimes is 6 months, and the lifetimes have a normal distribution. Now, like most companies, this one is going to offer a warranty period. So the company has chosen to offer a 42-month warranty. So that means if the customer's battery fails before 42 months, the company is going to pay them some amount because they didn't get their money's worth. If the battery lasts longer than 42 months, then the company is not going to pay back the customer anything the customer's battery lasted longer than the warranty period. And this is going to be a prorated warranty. So meaning that if the customer's battery, for example, fails at 41 months, then the company is going to pay him $2 back. If the customer's battery fails at 40 months, the company will pay him $4 for the warranty. If it fails at 39 months, the company will pay him $6 and so on. $2 for each month below the warranty period that the customer's battery failed at. I'm going to do three things. One, if we sell 1,000 batteries, I want to generate a histogram of the warranty payments that I made. Hopefully most of them are zero because the batteries would last longer than 42 months. But I will make payments to some customers and I want to generate a distribution, a histogram of those. Second, what is the company's average refund payment per battery sold? And third, what's the probability that the company will have to refund more than $6 for any given battery? Maybe this is my manufacturing and sales profit margin or something. So if I have to pay back more than $6 very often, the company may say, hey, this is not worth it. I need to do something different. So let's build this on a spreadsheet. First of all, I want to put the numbers that I'll need up here in a little box. The mean and the standard deviation, the warranty period, and the payment per month, I'll call it. This is not that you pay this amount every month, but that the how much the company pays for every month early that the battery fails. I was told that these numbers are 48 for the mean, 6 for the standard deviation, 42 for the warranty period, and 2 for the payment amount per month. Now let's generate a simulated battery life. That was said to follow a normal distribution, so I'll use a norm inverse function, give it a random variable, and tell it that the mean that I want is click here, and the standard deviation that I want is click here. I won't enter the numbers here so that if I want to change anything, I can change it one place and my formulas are still okay. And then let's calculate the payment, the warranty payment that the company is going to have to make based on that battery. So first I have to decide whether there is any payment at all. That is, did the battery fail before warranty or not? So how would I know that a battery failed before warranty? That is that if the warranty period is greater than the battery life, or another way of saying that is if the battery life is less than the warranty period. If so, then yes, there will be a warranty payment. Well, then how many months did it fail early? If I take the warranty period minus the battery life, that would give me the number of months that the battery failed early, and that should be multiplied by my $2 payment per month. Now, if this check is not true, then the battery actually lasted the warranty period or longer, and so the payment is going to be 0. So when I enter this, so let's show some examples of this working now. Here's a battery that lasted almost 44 months. That's bigger than the warranty period, so no payment was required. Recalculate. Here's a battery that lasted 41 months. That's a little below the warranty period. So take the difference between the two, multiply that by 2, and here's how many dollars I had to pay that customer. Not very much because his battery lasted almost the entire warranty period. Now, we are planning to sell 1,000 batteries here. So 1,000 trials of this. I'll number the trials so I can keep track of how many I have. And I want 1,000 of them again. So I think about right here. And get rid of a couple extra. And now, similarly to what we had before, the payment should be taking this information from cell B7. And now I'd like to have Excel fill out the rest of this table. So again, highlight the first row, do a Control-Shift-Enter to highlight the entire table. Go to a what if analysis data table. No entry for the row input cell, a blank cell for the column input cell. Click OK, and the spreadsheet fills it out. So notice again, most of these are zeros. Most of the batteries are going to last longer than the warranty period. A few of them fail early, and I have to make some payment to the customer for the warranty. The first part of the question asks me to generate a histogram. So I'm going to highlight the column of the payments and insert a histogram. So this should be comforting to the company. Notice, as we expected, the vast majority of payments, warranty payments, are small, less than 1. In fact, most of these are 0. And I see that there is some small probability that I'm going to have to make payments. It looks to me like the largest payment in my simulation that was made to a customer was less than $9. So that answers question number 1 for the company. For question number 2 and 3, I'm asked about an average payment and the probability that the payment is greater than $6. For the average, it really is just that. So calculate the average of these 1,000 numbers. And on this first trial, at least, I got a 1.09. And now, what about the probability that the payment would be greater than 6? So another COUNTIF command. These same 1,000 numbers are my range to count in. And then it's supposed to be checking if the number is greater than 6. And let's see. Oops, I entered a quotation mark in the wrong spot, I believe. Yeah, I didn't have one at the end like that. There we go. So in this simulation, the average payment was $1.02, and I made warranty payments to 61 out of the 1,000 customers. I called this a probability, actually, so let me take my count and divide by 1,000 to make it actually be a probability. So rerunning several simulations, I can see that my average payments are numbers like $1.12, $1.91, and $1.26, and $1.01, and so on. So it looks like around $1, maybe just a little bit more than that. And regarding the probability that I'll have to make more than 6 warranty payments, more than $6 for a given battery, 0.064 and 0.076, 0.068, 0.072. It looks like the numbers are between 0.065 and 0.07. So let me come back to the worksheet and fill in some answers. Here, the average was approximately $1. And here, the probability that there was a payment that was greater than $6 was approximately 0.065-ish, something like that. So this should be pretty comforting to the customer. It's not going to be paying $6 very often. And we'll stop there.